Swayam Prabha. Digital India. Educated India.
In the last couple of lectures, we looked at CTs, specifically the accuracy and the range. For protection CTs, we saw that the accuracy of 10% plus minus 10% or 5% has to be maintained up to 20 times the rated current if it's an IEEE CT, or we have different factors like 10 times, 20 times, or 30 times if it's an IEC CT. Now, the fact to remember there is that these the factor of 20, 10, 20 or 30 is for the AC current, is for the symmetrical AC fault current. For DC fault current, we will see today what happens if, because as we all know, when there is a fault, it will be accompanied by, depending on the time of or the instant at which the fault occurs, there will be a DC offset current, which could of course be 0, but that depends on the time t at which the fault occurs. We will account for the worst case of the DC offset current and see what happens to the CT in presence of the DC offset current. We have already taken care of the symmetrical AC current, and today as we proceed, we will see how to handle this DC offset current. We will also see the consequences of this saturation, and can something be done about it in terms of like we saw that the core has to take care of the flux that is generated because of the 20 times current. Can something similar be done in case of the DC offset current, and if not, then what are the alternatives? So let's proceed. We have studied this before in our power systems and other classes, that the fault current consists of a symmetrical AC component and a DC offset current. Now, how that occurs, we will try to derive that. Okay. Now, we will consider a transmission system with a source at both ends, though this equally well applies to, as we shall see, that it equally well applies to a source at a single end also, or a distribution system. So let's consider a transmission system with a symmetrical AC source at both ends, say E1. Let's say that fault occurs here, which is represented by a switch. And there is a source at the other end also. So for the sake of convenience, we have named it as E2. Okay, and the fault occurs at t is equal to 0. Okay, now the fault current will depend on three things. The first is, of course, the impedance up to the point of fault, that is the network impedance. Then the instant at which the fault occurs, t at which the fault occurs, and finally, though this is neglected, the current I or I0 that is flowing in the circuit before the fault occurs. This is usually the normal load current, which is quite or maybe orders of magnitude lower than the fault current. So, it can be ignored in most cases. We will also ignore it, but we will start our analysis including it, and then at an appropriate point we will drop it. Okay. So, now if you look at this circuit, this can be further reduced using a Thevenin equivalent to this circuit. Okay. This R and L are the Thevenin equivalent resistance and inductance, and you know of course how to do that. So, I will not repeat it here. The E or the Thevenin equivalent source is your normal AC source, Em sin omega t. E is equal to Em, where Em is the peak value and omega is the angular frequency. For generalization, we add a phase shift alpha. Okay. You can of course just do it with the Em sin omega t source also. Okay. Now, when the fault occurs or when the switch is closed, the fault current can be obtained as follows. I am not actually deriving the entire fault current expression, because you must have done it in maybe first year or second year AC circuits, but it is of the nature, if you see, it is of the nature, this V is a generalization, it does not apply to this circuit only, is R I t minus L d I t by dt. Okay. So, d I t by dt is equal to R by L of this form. Then you can, using Laplace transform, solve this. So, the current in this circuit, if you solve it, will be of this form, Em by Z sin omega t plus alpha minus theta. Now, this Z, what is Z? Z depends on R and L. It is R plus j omega L. Okay. And this Z of course is the magnitude Z, which is R square plus omega L square or R square plus X square. This is derived from the impedance triangle, and theta is equal to tan inverse of omega L by R. This comes from your impedance triangle, theta, R, omega L and Z. Okay. Now, we are not done with this expression yet. As you all know, the current through the inductor cannot change instantaneously. So, there is a current flowing in the circuit before the fault, that is the load current. This is that load current, and now this will decay with a time constant. Okay. Also, to offset this current, there will be a DC component which is actually opposing this. Okay. So, the minus Em by Z at t equal to 0. So, sine of alpha minus theta. This can of course also be written as plus, and you can change this to theta minus alpha. Okay. So, the expression that we have derived is sine of omega t plus alpha minus theta plus I0 plus Em by z sine of there is a sine of theta minus alpha. This whole expression, this current will decay with the time constant tau. What is the time constant tau here? Okay. Now, as you can see here, this current here IT consists of two components. One is a steady state AC component with a frequency same as the supply frequency omega, which is this is a rough expression. There is an AC component and there is a DC decaying component. Okay. So, there is a DC decaying component here. Now, if you see here, if you look at the time constant here, we will just have a short look at the time constant before we come back to this expression here, is that if you look at the time constant here, it is L by R, and if you multiply both the numerator and denominator by omega, you will get omega L by omega R, which is nothing but x by R by omega. Okay. Now, if you remember or if you recall, the x by R ratios for transmission circuits are very high. For a 400 kV circuit, it is of the order of 10, while for a distribution circuit, it is because the R dominates, it can be less than 1 also. It is usually of the order of 0.8 or so. Now, if you take this time constant for a 400 kV circuit, and these are approximate calculations, of course, and then you plug in 50 hertz here in the omega, then you will get 100 pi. This is roughly of the order of 30 milliseconds. Okay. And you know that this decays because this is an exponential decaying term, it decays as 1 by CE, where C is an integer 1, 2, 3, etc. So, if you plug in C here, for one time constant, you will get about a 63% reduction, and rather it reduces to 63%, and by the time this totally dies out, it is about 4 to 5 time constants. Okay. So, you can see here that that for a transmission circuit, this is a issue, because 30 milliseconds into 4 or 5 times means it takes about 100 or 120 milliseconds for the DC offset current to die out completely or almost reach a 0 value. Now, to avoid that, we need speed in relaying. So, this is again ties to our initial attributes of relaying, where we said that speed is essential. Okay. Whereas, on the other hand, for distribution circuits, since the x by R ratios are very low, speed is not so much of importance. So, that is why we do not talk of much of high speed relaying in distribution circuits. Now, coming back to our expression of the current here, we will write it again here. Em by z sin omega t plus alpha minus theta plus I naught plus Em by sin t raised to t by tau. Okay. Now, this will be maximum at t is equal to 0 when alpha is equal to 1 or minus 1 also. So, which implies that alpha minus theta is equal to or sorry, when sine of alpha minus theta is 1, which implies that alpha minus theta or theta minus alpha is plus or minus pi by 2. Okay. And the second condition is the initial current flowing in the circuit is also greater than 0. Now, this is usually ignored, because as we said the fault current is maybe 1 order or 2 orders of magnitude higher than this current. So, this can be ignored. This is one assumption that we make here. So, this IT expression can be simplified to Em by Z sine of omega t plus minus pi by 2, or rather I will because this is we have said theta minus alpha. So, I will change this to minus plus plus minus Em by Z e raised to minus t by tau, which can be further. I am dropping the magnitude expression. This Z implies that we are talking only of magnitude of Z sine of omega t minus plus pi by 2 plus minus e raised to minus t by tau. Okay. Now, this is the fault current which is flowing in the transmission circuit. Our CT on the other hand or the to be more precise, the relay sees the secondary current. Okay. So, now this we have to transform into the secondary current of the CT. Now, for convenience let us label this as IP, because this is the current flowing in the primary of the CT circuit. Now, IS will simply be, again this I am dropping the expression T here just for the sake of convenience, is just IP by N. Okay. So, this current divided by the turns ratio, ignoring the excitation current, we will get IP by N. Now, if we just concentrate on the CT secondary circuit here, okay, this is IP by N, okay, and this is the secondary burden. Okay. Now, this includes the CT leakage reactance and all that, okay, and then this is the voltage developed across the CT secondary. Okay. Now, this VB is simply given by ZB into IS, which is nothing but P by N. Now, from the transformer theory, we also know that VB is equal to N d phi by dt, because now we are interested in finding the effect of this current on the core and whether the core saturates or no. So, we need to find the flux. So, now we need to somehow link the expression of this voltage with the flux. So, this is the transformer equation is what we will use to do that, and so just rearranging the terms, we will get N d phi is equal to, now to find the flux that is accumulates in the flux to find the flux that accumulates in the core over a time period t starting from 0, we have to integrate this. Okay. So, we will get 0 to t d phi is equal to 1 by n integral 0 to t VB dt. Okay. Now, what is the expression of VB? We have VB here and its dependence on IP. The expression of IP we already have here. This is the expression of IP. So, we will plug all this in and get a nice expression for phi t or simply phi. Okay. Again, this we can assume that the remnant flux is 0, that is again for convenience. The remnant flux or phi 0 need not always be 0, but for the sake of our analysis we can assume that it is 0. Okay. So, now all the constants we have collected, what this k is we will come to very shortly. Okay. So, then we get k, I am just rearranging the terms e minus t by tau minus. Now, what is sine of theta minus 90 or plus 90? It will simply give you cos. So, this will be cos of omega t dt. Okay. This k is, what is k? Z b E m z upon n square. Okay. So, I am just that is just a collection of the terms. Okay. So, we will proceed from here. Now, what is the integral of e raised to a t? It is simply e raised to a t by a, integral. Okay. So, let us treat tau as a, and since we are ignoring the residual flux or the remnant flux and dropping the expression t, we will get this integral as k by a you can evaluate this integral and see this is at t equal to 0. Okay. K by omega sine of omega t. Now, as we saw in the expression of the current, the flux 2 consists of two components here. One is a transient component which decays with a time constant tau, and one is a steady state or component which has the same frequency as that of the supply, okay, omega. So, this you can call it as a DC flux, and this is an AC flux. Okay. With the peak value of the DC flux is k by a, and the peak value of the AC flux is k by omega. Now, if you were to take the ratio of these peak values, then phi DC by phi AC is k by a divided by k by omega, which gives you omega by a. Now, a is 1 by tau, which in other words gives you omega L by r, which is nothing but x by r. Okay. Now, if we were to see the total flux as a fraction of the AC flux, then what will we get? Phi AC plus phi DC upon phi AC is equal to 1 plus x by r. Okay. Now, what does this imply? This is also known as the oversizing factor. What it implies is, if I were to account for the DC flux also in the sizing of the CT as compared to only the AC flux. I am sorry, I will just make this a bit clear. Phi DC plus phi AC, okay, upon phi AC. Now, we have already accounted for the AC sinusoidal flux when we did our sizing for 20 times, 30 times, etc. Okay. The DC flux is not accounted for, okay, in that oversizing. So, if we were to size the CT core to take care of this DC offset flux as well, we would have to oversize it by this amount. Okay. One is what we have already done for the AC flux plus x by r. Now, you can imagine that x by r for a 400 kV circuit is around 10. So, we would have to oversize the CT 11 times, or even worse, for a 765 kV CT, the x by r is around 20. So, you will have to oversize the CT by around 21 times. So, this will make it unviable economically, because and also the physical dimensions will increase by quite a bit. So, one way of getting around this is to avoid the CT saturation in itself at the source itself. So, to make the relay acting as fast as possible. So, we will go back to the slides deck now and have a look at what happens when the CT saturates. Okay. This is what we covered. This is how the fault current will look like. Okay. I did not draw it there, but there is an AC sinusoidal component which you can see clearly, and the frequency is the same as the supply frequency, and you can clearly see a DC offset component also here. Okay. So, the equation for this we derived. Okay. So, this is what happens when the CT saturates. Okay. We have seen that the coupling between the primary and the secondary is lost, and the CT starts behaving like an air cooled CT instead of an ion cooled CT. So, it does not, the secondary will not faithfully replicate the primary current, and that causes what is known as the blinding of the relay. In other words, the relay cannot take a correct decision, it is blind to what is happening in the primary circuit. So, what happens actually is, you can see here the secondary current instead of being sinusoidal, it is a little peaky in nature. You can see that it follows, I will just draw the flux. The flux accumulation actually, if we take 0, this is the flux in the core versus time, it is something like this, okay, because it accumulates. Okay. This is sinusoidal, of course, even though it may not appear like that, it is sinusoidal. So, what happens is, in the in this case, because we are talking of we have taken it as the positive values. So, that in the negative half cycle, the CT may come out of saturation. Okay. There it faithfully replicates the sinusoidal part. Okay. Here you can see that in the initial part that it replicates the sinusoidal. Here it goes into saturation. Okay. So, what would have been this gets clipped. Okay. Then the value, the coupling is lost, and you get this kind of waveform. Okay. Then here again it comes out of saturation. Okay. In the negative part it comes out of saturation at around this point, then it follows the sinusoidal flux path. So, you can see that because of the peaky nature of this current here, that the RMS value will be much lower than were it to be a sinusoidal current. Now, this lower RMS value will cause problems in our relaying, because it will an overcurrent may not be read as such, or if it is a differential relay, then it would cause tripping. In an overcurrent relay, it may even though the fault current is high, it may cause a no trip situation. In a distance relay, similarly, which measures apparent impedance, we will see that when we come to distance relays. It measures apparent impedance, that is V by I. Since I is smaller, the impedance might be larger and it may not come in its zone. So, it may not see a fault when there is a fault. On the other hand, in differential relays, even though the fault is not in its zone, if one CT saturates, then if one of the CTs saturates, then you may see a fault when there is no fault. So, both kind of situations can occur. Okay. So, okay. So, we will have a quick look at what CT saturation can lead to. Let's consider a bus fault, okay, a bus fault relay or a bus fault situation where we have CT. We are not actually drawing the relays here. Say there are three. We are taking an extreme example here just to illustrate the okay. Say these are 1000 by 5 CTs. And this CT on the other hand, because it is a summation of, it has to carry all the three currents, it is a 3000 by 5 CT. Now assume that there is a fault here. Now this is a fault which is outside of the zone, okay, which is outside of the bus zone, and in normal circumstances you should get I1 plus I2 plus I3 plus or minus I4, that depends on is equal to 0. So, the Kirchhoff's law should apply. This I1, I2, I3 are these currents, I1, I2, I3 and I4. Okay. But now consider that this is of course in the normal situation. Now consider that there is a fault which is beyond this CT, but what happens is that these CTs because of the flow of the fault current, the voltage, if you can see here, developed is around 1/3 of that developed here, okay, and the fault current is the same, okay, and as a consequence this CT may saturate, okay. We will have to look at the ratings of the CT and etc. to see, to make sure that that whether that CT saturates or not, but for the sake of this example, assume that this CT may saturate, while the voltage developed here about 1/3. Okay. So, maybe these CTs will saturate less or may not saturate at all, in which case what happens is this equation no longer holds. Okay. I1 plus I2 plus I3 plus I4 may not be, will be equal to some value, okay, which is not the fault current, but may be equal to some value, and which may be enough depending on how your relays are set to issue a trip command. Now, to avoid that, there are techniques known as CT stabilization techniques. Okay. CT stabilization techniques. We will not look into that now. Maybe we will look at it when we do differential protection later towards the end of the course. But there are various methods in which you can avoid this. Of course, one method that we earlier saw and which is also used is that to make the relays as fast as possible. That is why you will find that the bus differential relay sometimes use a sample to sample comparison, where you need not wait even for one full cycle to do a phasor computation and then compare the currents, etc. They can be as fast as quarter cycle or half cycle relays. But those keep in mind that they do not do a phasor computation, but rather do a sample to sample comparison, which is okay for the application that they are meant for. There is also, if you see we'll take an example of a line differential relay here, that there is a transmission line. We will of course see this in greater detail when we see differential protection. You don't simply do, we saw this briefly, this is a sensitive overcurrent relay. Okay. And what we do is, you are aware of the dot convention, you must have studied it in your earlier classes, is that it simply says that, say this is the I sending end and this is I receiving end. When the current enters the dot here, it leaves from here. Okay. So, if you do this, then a circulating current will be set up here, and the same current S we have already used. So, let me use IS dash, and if the ratios etc. are perfect and we have selected the CTs properly, then there will be no current flowing in this part. Of course, that is not the case. There are charging currents, the CTs may not perfectly match etc. So, there will be some current flowing through this. To avoid false tripping or nuisance tripping, there is a restraint function also which is provided, or the restraining current, which is generally the average of the current IS plus IR. Let us take I1 and I2 for or maybe IS plus IR, we can stick to that upon 2. This is the restraining current, okay. And the differential current of course is IR, okay. So, now this is how it looks on a graph. I differential and IR. Okay. So, usually instead of providing a single slope, this is provided, a bias differential kind of characteristic is provided, where you provide a variable slope. I have just drawn 2 slopes, but you can have even more sections of or different slopes if your application so demands. Now, you can if you see this versus time, and if there is no saturation, because this is a function of time, the flux does not instantaneously reach that value that we earlier saw. It accumulates in the core. So, if you see it as a function of time, the 2 currents or the 2 CTs, if there is a fault say at the remote end, okay, when there is no saturation, the currents will be almost similar to each other. So, you will have the restraint current earlier increasing, okay. And if say one CT saturates after this, then it will go into this region. Now, this is the restraint region and this is the operate region. Okay. Now, as you can see here that the restraining current increased in the earlier part, and then suddenly it shot up and the differential current increased. Now, if somehow this characteristic or this locus could be tracked, which is easy to do in a numerical relay or the set of numerical relays that you are using for the differential protection, that you could then avoid tripping. See, there are now, if you notice, there are 2 parts here. One is that we say that speed is of the essence here, because you do not want the CT to saturate, and if you want it to detect a fault early on before the saturation occurs. But there is a second aspect that we have, that is the security aspect, is that after a passage of time, depending on the flux accumulation in the CT core, if the CT saturates, the relay will anyway detect a fault even when there is no fault. Okay. So, one is the dependability aspect where you need to take a quick decision if there is a fault. But if there is no fault also, you have a problem that one of the CTs could saturate, and then the differential current could increase, and then the relays would issue a trip command. So, to avoid that, we have stabilization techniques etc. But this is one thing as relaying engineers that you have to keep in mind, that while the speed is of, you need the relays to take a quick decision. After a passage of time, the relay will anyway detect a fault, okay, even when there is no fault, if the CT saturates, of course. So, that also has to be avoided, and the security aspect also has to be kept in mind. Okay. So, we will quickly look at the remaining portion of the slides. This we saw the CT oversizing factor or the core oversizing factor, and we saw that how impractical it is. So, these are a few precautions which have to be kept in mind before while we select a CT or specify a CT, that the continuous rating, the CT rating and the continuous load current should match. We saw that example of 1000 by 5 and 3000 by 5, those are the continuous currents, continuous rated currents. The fault current for which it is rated is 20 times the CT rated current. This is of course the IEEE specification. The IEC specification could be 10 times, 20 times or 30 times. That is the maximum current, primary current till which the accuracy of the CT can be maintained. The voltage rating of the CT should be compatible. This is more from the insulation perspective rather than the current transformation perspective. And it should also be ascertained that the magnetizing current is kept much below the pickup value. This is of prime importance, especially in differential protection, also in overcurrent protection. So, that concludes the CT part. We will have a very quick look at the voltage transformer equivalent circuit before we close for the day today. We will not be able to complete it in today's lecture, but we will get started in any case. Now, unlike the CT where we made certain modifications to account for the fact that the CT primary is a current source instead of a voltage source, a voltage transformer is exactly similar to that of a power transformer. The equivalent circuit especially is exactly similar to that of a conventional power transformer. Okay. There is a difference, of course, we will come to that. The need of a voltage transformer is of course where you need to give voltage inputs to the relays. As we all know, the primary voltages in transmission and distribution are high. In transmission circuits, they could be 132 kV, 220 kV, 400 kV, 765 kV, and in distribution circuits could be 11 kV, 22 kV, 33 kV, and there are some states in India which have a sub-transmission voltage of 66 kV also. Now, as you can imagine, these are very high voltages, or they are also classified as extra high voltages, and the relay cannot take this input. So, to step down the voltage, which is standardized to 110 kV, 110 volts for relays, which is the PT or this VT secondary. VT is the voltage transformer, also referred to as the potential transformer or PT. So, this is standardized at 110 volts line to line, or line to ground is 110 by root 3. Like that, like in a CT, the CT secondary is standardized to 5 amps or 1 amp. Here in VT secondaries, they are standardized to 110 volts. Okay. So, this is the equivalent circuit. The one that you see on the slide is the equivalent circuit of a voltage transformer or a potential transformer. You can see that it is exactly similar to that of a conventional transformer. Okay, no difference here. Only thing is that the rating here is very low. In a power transformer, you have it rated in kVAs, maybe 100 kVA, 300 or 315 kVA, 630 kVA, 1 MVA, and so on and so forth. The largest transformers are in 500 MVA or so. Okay. Here this is rated in VAs, okay, 30 VA, 60 VA, like that. Okay. So, that in that sense it is low power rating transformer. Now, as we said that the secondary voltage has to be 110 volts, okay, and if you see the primary, it can be, as we said, in transmission circuit, it can be high as 220 kV, 400 kV, even 765 kV. So, this ratio would be very high, okay, the turns ratio, and the transformer because of that would become very bulky. To avoid that, what we do is we use a voltage divider. Of course, that does not mean that these are not used at all. these are known as electromagnetic VTs or electromagnetic PTs, EMVTs or EMPTs, where there is no voltage divider used, and it is very similar to a conventional transformer. So, we will come to that maybe next time where they are used. But in a conventional, that is the conventional VT, in a capacitive voltage transformer or a coupling capacitor voltage transformer, the voltage divider is used. Now, the voltage divider is we will just see the concept before we stop, and then we will continue next time. So, instead of a resistance voltage divider, a capacitance voltage divider is used because it is more economical here in this application. C1, C2, this is the line voltage here, say V, okay. This is the ground, and here what we do is, this is of course not the entire circuit, that we will see next time. Okay, this we can show it like this also. Okay, for convenience I will remove this. I have just drawn it like that. Okay, this is say AS21. This is a conventional VT. Here this is a capacitive voltage transformer. This line voltage could be any, because this is a phase to ground, we will show it as 400 by kV by root 3. Okay. This transformer usually is 11 kV by 110 volts. Okay. That is the turns ratio. You can, if you take it line to ground, it will be 11 kV by root 3, 11,000 by root 3 is to 110 by root 3. Okay. We will analyze this further during the next lecture. Okay. We will stop at this. This is where this is the equivalent circuit of a capacitor voltage transformer, as it is known, because you have a capacitor voltage divider, capacitive voltage transformer. I am sorry, there is a mistake here. So, this uses a capacitance voltage divider, and that is why it is known as a capacitive voltage transformer. It is also known as a coupling capacitor. The reason for that, coupling capacitor voltage transformer, which we will see in the next time why it is known as a coupling capacitor voltage transformer. We will quickly see how to analyze this. If you have to find the Thevenin equivalent, of course, you will have to short this to short the voltage. This is the voltage source here. So, you short this to ground, you will get C1 in parallel with C2, which is nothing but two capacitors in parallel, C1 plus C1 in parallel with C2 will give you an equivalent capacitance of C1 plus C2. So, you will get in the primary circuit, you will get a voltage source and a capacitance this is a transformer, this is a secondary leakage impedance, this is the burden, and this is 1 upon j omega C1 plus C2. Okay. Now, as you can see that this capacitor will cause a phase shift in this voltage here. If this is the source voltage, it will cause a phase shift in the source voltage, which will not lead to a faithful reproduction of the voltage here, of the voltage on the relay side, which is what we need. So, to avoid that, we will use we will see what is done to avoid that in the next class. So, we will stop here. Thank you.